In this video, we're going to talk about gravitational fields. While the force between two objects can always be computed by using the formula for the gravitational force, it's sometimes convenient to consider one mass as creating a gravitational field and the other mass responding to that field. In our material so far up to this point, that gravitational field would actually be the acceleration due to gravity, or the lowercase g. So let's take a look at how we end up getting that. We know that the force here is equal to g m1 m2 over r squared. There's no vector signs here, so we're looking at the magnitude only. Now what I'm going to do is I'm going to look at what's acting on m2. And so I separate this out. Okay. Now I'm going to replace this with the mass of the planet, which is the Earth, and this is being just a generic mass of just any object. Now we know that the force on the object by the Earth is equal to your weight, which is equal to mg. And there's the m. So that means that this piece right here must equal g. So the acceleration due to gravity, its magnitude, is equal to the universal gravitational constant times the mass of the planet divided by the distance between the center of planet and the object squared. Okay, that's the tricky part. This is not necessarily the radius of the Earth. This is the orbital radius. So if the object's sitting on the surface of the Earth, this would end up being the radius of the Earth. However, if we're looking at a satellite, which is 100 kilometers above the surface, or 300 kilometers above the surface, then we would have to add that amount above the surface to the radius of the Earth to get what this r actually is. Okay, so we're going to do some examples so you can see that. Okay, the magnitude of the gravitational field created by an object varies from location to location in space. It depends on the distance from the object and the object's mass. The gravitational field G is a vector quantity. So that means it's the acceleration due to gravity, and we're going to go ahead and put a vector sign on that. Its direction is always toward the object that creates the field. That's the direction of the force that a test mass would experience if it's placed at that location. In fact, G is the acceleration that a mass would experience if placed in that location. So here we're looking at the magnitude because there's no direction here. Okay, so looking at this diagram, where is the gravitational field the strongest? Is it going to be at A, B, C, D, or E? Okay, so let's check and see if you've picked the right answer. The correct answer is A. How do we know? A is the closest. Look at the vector. It is the longest. What happens to the gravitational field if the distance from the center of an object doubles? Okay, so you're going to have to go back and look at the formula for this one. Go ahead and pause the video. Okay, so let's take a look at the answer. It should be D. It is cut to 1/4. Remember that G is equal to M, capital G, over R squared. So if I double the distance, it becomes 1/4. What happens to the gravitational field if the mass of an object doubles? Okay, so let's see if you have the correct answer. It is A. The field will also double. In the next video, we'll talk about surface gravity.